Hello everyone, welcome back to Ram Circle class. So we have been moving on the third chapter of NCERT, that is current electricity, and we had reached some relations regarding the relation between current and drift velocity. So drift velocity was one of the most important topics so far we had learned in chapter 3rd, and that has been related with the current, that is I, and I is what? The charge flowing per unit time through any particular area. Today we shall move little more ahead of that. These are going to form some conceptual ideas regarding the resistance of any conductor. Okay, so in the last time we had a relation, that is current and drift velocity, and the current was given by I equal to MEAVD, where M is number density, that is number of electrons in per unit volume of the conductor, and this is always in the order of 10 to the power 27 or 10 to the power 28 electrons per unit volume. And these are the common symbols, that is charge on electron, area of cross section of the conductor, and this is what? The drift velocity. And further we have that V equal to force on a charged particle divided by mass, that is acceleration of the charged particle, and this is multiplied by the relaxation time. So these are the two very important relations so far we had developed or derived. Now if we put this value in I, what we get? I is equal to NEA, and then put the value of drift velocity over m into tau. So this is giving you NE square AE over m into tau. Okay, very simple, two relations, and put the value of drift velocity. So we got this relation. So this is going to play some crucial roles for us. If we have a conductor, consider we have a conductor of this sort, of length L, area of cross section A, and this is connected by a battery which is supplying a potential of V, so that the electric field set in the conductor is equal to E. Okay, and we know that this electric field is what? Potential per unit length, that is NE square A over m tau, and E can be written as voltage developed across the ends of the conductor and divided by this. So this is going to be new relation. See how. So if I take this I in the denominator and replace everything from here on the left hand side, so by cross multiplication I get ml over NE square A tau is equal to V over current I, right? So now see carefully, this is very important. This is what? Mass of the moving particle, and here the particle is electron, because the ions which are quite larger in size cannot move, leaving its own site in the conductor. So only electrons are allowed. So this is mass of electron, which is constant. We are not going to take the idea of relativity, or relativistic mechanics is completely discarded, because we are discussing about the classical physics. So mass will remain constant. In relativity, what we take? Mass varies. So that's idea is completely not being taken into account here. So we shall be putting our focus on classical physics. Okay. So again, mass of the electron, length of the conductor, and this is number density of electrons, charge on every electron, area of cross section, and tau depends on what? Temperature. So if temperature of the conductor remains constant, then what happens? The tau will remain constant. So if temperature of the conductor remains constant, then tau will remain fixed, and rest of the quantities for this particular conductor will be constant. So obviously the left hand side completely becomes a constant. That is V over I is equal to a constant, and according to Ohm's law, that constant is known as what? Resistance of the conductor. So V over I is equal to constant, and this constant is known as resistance of the conductor. This is what we know as Ohm's law is. So this giving you R is equal to ml over Ne square A and tau. See, this is equation number 1. From the previous knowledge, what we know? Resistance of any conductor of length L, R, is equal to rho L over A. Well, LA is what? The area of cross section. L is the length of conductor, and rho is what? Its internal property known as resistivity. So comparing this is again resistance and this is resistance. So what we get? This now see, this is L over A. So this is finally giving you rho is equals to m over n E square and tau. So rho m over E square and tau. So this is the expression for the resistivity. So this is telling us the resistivity of any conductor or any matter depends on what? Mass of the electron, which is constant for every conductor, charge on electron, which is again constant for every conductor, but number of dense electrons per unit volume, and tau will be different for different materials. So rho becomes different for different materials. For example, copper will have larger number of what? Free electrons in comparison to that of any semiconductor like silicon or gallium. So if N is larger, for example any metal, mercury, iron, gold, silver, N is very large. So if N becomes large for any particular temperature I am talking about, then rho will be low or least. If N is large, then rho will be less and less. So that material becomes more conductive. So if resistivity is depending on what? Number of electrons per unit volume and its relaxation time of the electrons. So guys, this is very important relation. Note it down. Now in the further, we shall discuss how N and relaxation time affects the resistivity, that is on what factors the that is relaxation time is going to play a vital role to change the conductivity or resistivity, and then further resistance, because R depends directly on what? The resistivity. At particular constant temperature and particular physical dimension, that is L and A will fix, and if temperature is fixed, then this quantity remains fixed. So this R becomes again a constant. We are going into what? V over I equal to constant, that's giving you what? Ohm's law. Okay, so this is very clear and intuitive that there should be no doubt regarding this. So we have obtained this relation, and this is simply giving what? Rho is directly proportional to 1 over n, or inversely proportional to n. So if n increases, the rho decreases. That is, if n increases, then rho decreases. Okay, relation number 1. Case number 2, rho is again inversely proportional to relaxation time. That is, if relaxation time decreases, we shall discuss how can it be decreased or increased. If relaxation time decreases, then the resistivity will increase. So these are very obvious relations between the two factors, and now we are going to discuss how generally this value of n remains constant for most of the conductors at a certain number of temperature, or I can say at a certain range of temperature the n remains constant. So only thing that is changing, that is relaxation time. So you know that the drift velocity is given by this, right? So drift velocity will increase only if what? Electric field increases, and electric field increases because of applied potential. So when this electric field increases by the application of this battery or higher value of battery, then electrons speeding up and then colliding more frequently with the other electrons and the ions. Agree? That is, mind this, if drift velocity increases, then electrons have frequent collision with the other bodies inside the conductor. If the frequency of collision increases, then obviously tau becomes low, and if tau becomes low, then what we get? Resistivity increases. So if the drift velocity increases, along with temperature, electron will gain more what? Electric energy, simultaneously thermal energy, because temperature increases thermal energy, so their thermal velocity increases. And what this potential is doing, that is providing it a particular direction. So simultaneously both the things if get combined, then electrons collide more frequently, reducing relaxation time, and if relaxation time decreases, then obviously resistivity increases. So that's the very important fact, please note this down. Okay.